So welcome back. So let's have a look. Where are we going? So we did this one, and then we're going to look at somewhere it's not quite so symmetrical now. And hopefully ask you this question. Yeah, use the method of calculus as... Oh, you want to see it?
I think I do.
Okay, if you insist. There you go. So, using the method of Gauss's law that was shown in class, determined the electric field 2 meters from an infinitely long string of positive charge that has a linear density. If we look at it, it's a weird equation, isn't it? It's got Ke in it, it's got this lambda in it. Lambda is the charge per unit length, and it's got this separation in it. So let's go and let's just have a look at this. So the first thing we do is we just basically get a pen and we draw ourselves the wire. And then we take a point of interest. So we'll do the point of interest there. And we say 2 meters from an infinitely long. So that's my 2 meters, and that's my R. And that's my point of interest. And I want to make up a Gaussian surface that would work for this. So I'm going to basically, I can't do a sphere, but what I can do is a cylinder. I'm going to draw it like that so it's a bit more. So it's like that. Then I have my little window, of course, and here, because I am a constant, I'm recording. So because it's a constant distance from this line of charge, my E is constant, and my E is also perpendicular to dA for this sleeve. Now, frankly, what about this surface here? On that surface here, my electric field is perpendicular to my dA. And the same goes for the bottom one. So I'm going to divide this up into 3 sections. There's the top face. There's the bottom face that I can't really see. And then there's the sleeve around the edge. And if I say my Gauss's law, flux is equal to integral of vector E dotted with dA, which equals Q inside over epsilon naught. And if I recognize that for the top, let's call this A. No, let's not call it A because we have an A kicking around. Let's call this surface I. And let's call this surface II, and let's call this surface III. So for I and II, for those 2 surfaces, we can say that E is 90 degrees to dA, which gives the EdA cosine theta equals 0, because that, my friends, goes to 0. Yeah? So we went the other way. Rather than saying we want E to be parallel to dA, we said, well, if we can't have that, we'll have E perpendicular to dA, so that it can be 0. So I don't need to worry about the top and bottom surface. And then I say, well, for 3, I'm going to say that flux is equal to, I'm going to say that E is parallel to dA, which gives me the E dA cos theta, that goes to 1, equals E dA. Because they're parallel. So I'm going to say, well, in that case then, and also I'm going to say that, well, let's do it in steps. So my flux is equal to, it's going to be the integral of just E times dA, which equals Q inside over epsilon naught. And I'm going to say, well, also, E is constant on Gaussian surface sleeve. So my flux is equal to E integral dA, which equals Q inside over epsilon naught. And my surface integral of dA is equal to, it's going to be pi, it's going to be pi, it's going to be 2 pi r times h, where this is h, or L, or whatever you want to call it, but this is h. It's the circumference times the height. So then we say, well, E times 2 pi r h is equal to Q inside over epsilon naught. So E is equal to Q inside over 2 pi r h times epsilon naught. Let me just dip back for a minute. I can't remember if it's left in pi r's. I can't remember if it's left in epsilon naughts or KE's. It's in KE's, okay? So I'm going to say KE is equal to 1 over 4 pi epsilon naught. I always have trouble with this bit, and what I've learned to do is I say epsilon naught is equal to 1 over 4 pi KE. So E is equal to Q inside over 2 pi RH, and then I'm going to put 4 pi KE. So E is equal to 4 pi over 2 pi is 2 KE Q inside over, that 2 pi went away, RH. Now, Q inside is equal to H times lambda, where lambda equals Q over L. Sorry, Q over H. That there is my lambda. Q over L, we should say, which equals 6 coulombs per meter. Oh, I see. So I can say E is equal to 2 KE, and then I have H lambda over HR. So E is equal to 2 KE lambda over R. That's it in letters. So this equals 2 times 6 over, how far were we away? 2. KE, which equals 6 KE newtons per coulomb meter squared. Cool. So very different, but somehow the same. We're using those same rules. We're basically saying let's try and get E constant on our surface, or 0. Let's try and get our E parallel to dA, or perpendicular. And in this case, for the top and the bottom, we said, well, E is perpendicular to DA, so they can go away. But then around the sleeve, E is constant. It's kind of nice. Now, the intelligent thing is, the thing that would be, the clever thing was the first person who decided that that was their Gaussian surface. For us, we kind of like, we're learning the pattern. So for us, it's more a case of, oh, look at that. Yeah, this is why we did it. But for the first person to come up with it, would not be trivial. It's not like, you know, somebody who's never seen this before should just be able to do it like walking off a cliff. It's, you know. The next example, which I'm not going to do, is this. It's in the homework videos. I would not ask you this as a test question, but basically it's again, it's playing with non-spherical symmetry. Okay. So if you're curious, then look through that video and figure it out. But basically, it's saying E is equal to, and this is an area density, whereas the other one was linear density. This is an area density. Okay. And basically, you're going to figure out, of course, that your area vector is in that direction. So you can forget about the sleeve in this case. The only thing that counts are these two areas at the ends. One on one side of it and one on the other side of it. They're the only two that count. And so you can, you know, and for those, the E is parallel to dA. So our area is 2 times pi r squared for that. So it's not hard. It's just, you know, unless you've seen the Gaussian surface, it's hard. You know, sitting there and thinking, now what kind of Gaussian surface would do this? I think that takes experience. Whereas if you've seen it, you kind of go, oh yeah, this is where we use the cylinder, you know. So basically, let's look back. This is fair game. The one on the inside or the one on the outside, fair game, but the trivial answers in the end, it's 0 and it's the usual. That's fair game. The one on the inside is fair game. So I'd say if you were to, you know, it's not to say that the others will not come up, but I think if the others come up, they're a bit of a gift. But the ones where I think it's more demanding is this one here and that one there. I think those are the two where there's more steps and there's more stuff to it, you know. Almost there. So, conductors in electrostatic equilibrium. So we have this idea that we can draw. So this is a conductor. This is a metal. All the charge sits on the outside. It's not the same as a ball of charge. Ball of charge somehow has charge all the way through it. This is a conductor which has charge on it. So although it's not hollow as far as the charge is concerned, it is. There's no charge on the inside of it because why would you have charge on the inside? They all want to get away from each other. Okay, so it's like that. And what you find is when you draw these field lines, they always approach at 90 degrees or leave at 90 degrees. This has got positive charge inside, so they're leaving at 90 degrees. And then we have these field lines, and the field lines tend to congregate near points. So the electric field is very strong near a point. And that's really useful. Because if I want to literally spray charge, I can have a comb of needles. And if I make those points nice and sharp, when I make this say positive, it will spray charge, or negative, it'll spray charge. Let's think about negative. It will spray charge. And we use that an awful lot. We use that in flat panel TVs. Use these electron emitters. And in a Van de Graaff generator, where you want to spray electric charge onto a belt, you use these. In a photocopier, you use these to spray the charge onto the drum. Or maybe take the charge, well, anyway, it depends how it's designed. On the old, very old ones, they'd spray the charge onto the paper. but they don't do that so much these days. They probably still do when I think about it. And lightning rods, actually, so in lightning rods, the common misconception is that a lightning rod is there to conduct the lightning to ground. And there's so much current in a typical strike of lightning that it's hard to imagine a piece of wire could easily withstand it. So the trick with lightning rods is that you want to discharge the land or the building before it becomes struck. The lightning will not strike a discharged object. The lightning, say, is positive, and it's looking for a negatively charged object. And if it sees the negatively charged object, boom, it's going to go for it. So the thing you want to avoid is the tree that's charged, or the hill that's charged, or the building that's charged, because they're going to be struck. And so anything you can do to dissipate charge is better. And so it was actually good old Benjamin Franklin realized that if he took a metal rod and put a point on the end to it, it tended to discharge. And so if you put a point on the end of your building, it won't be struck. And so one of the ironies, I'll tell you this more next time, but one of the ironies is that when Benjamin Franklin came up with that, Britain was not ready for American upstarts to be good at science. It was like, it's bad enough that they just revolted against Britain and took the continent away. So they had a tendency to say, well, we've already thought of that, you know. So Benjamin Franklin came up with a lightning rod, and Britain came up with a lightning rod that they'd already discovered, which was actually like that. You know, just make it look different. Well, ironically, this is lousy at discharging things. It's not good at discharging things at all. And so that's the worst of all worlds. If you put that on top of your building, it's going to hold the charge up and say, look, I'm charged. Come and get me. So the British lightning rod was actually the worst kind of lightning rod possible. And the American one worked, actually, which was one of those things. Cool. So let's call it a day there. Let's end there. Oh, okay, I'll go on then.